Hello and welcome back to the Geostatistics course for beginners with QGIS and R. This is the 9th lesson of this course, and today is going to be the last lesson related to univariate analysis. The next lesson is going to be about bivariate analysis. Today I would like to start making an explanation about how you can create a help menu related with your scripts. In this case, we are going to select number 6, that is histogram count bins. Double click, and as you can see, we can take these windows to provide information related with this script. Then we can add a description, and also we can add information related to the mean of all these parameters and how this information has to be filled in order to have a successful result. Also, in these windows, we can add information related with the person who create the script, also if there is any helper, also the version, and a lot of information. Let's go to start. To create the file, we are going to use Notepad. Notepad is a software or application that it comes by default on Windows 10, but you can download it if you have another different software for your system. Then I'm going to open this one, double click, and now I'm going to save this one. That is important, save as. You have to keep the same name as you have here. Then what I'm going to do here is open this one with the right click of your mouse, then go to edit, then press this button to save as. Then we know it's number 6, then going to take this name over here, copy. Now I can close this one, I can close this one, and I can go over here and save with this name. I'm going to leave at the moment this one, text at the end. Paste the name over here, and I'm going to save on my desktop. Save. Going to check everything is good. Okay, is this one. Double click. Now I'm going to add the information inside. I'm going to paste the things I did already, and I'm going to explain a little bit how it works. All the information has to be inside of this type of brackets. As you can see, this one at the beginning and also this one at the end. Then for the description, we have to add this sentence between quotation marks followed by colon. Then we can make the definition of the script. You can add any information. In this case, I added a histogram with the number of samples per bin in a specific range. Then also, as you can see, we have also quotations here and quotations here. Then comma. Then it separates just one section, okay? Then for the second definition, we are going to use this sentence, and that's the name we want for the script, right? And here I added a histogram count bins. And the second one is layers. Then we can follow this order as here. Then here we have layer, parameter, label X, and the names has to be the same as here, okay? If here we have layer with capital letter, the first L, over here has to be the same. As you can see, layer started with the L capital letter. Then we have parameter. And if you check over here, we have parameter. For label X, if you want to separate, you have to put a lower dash. I'm going to show you here. For the label X, as you can see, I added a lower dash in this case. And that's it. For example, for layer, I have the same quotation marks, then layer inside, then colon, then quotation, definition of that parameter, and then finish with quotation and comma to separate. Okay, that's the way we are added any section from here. Okay, parameter, label X, label Y, title graph, and then we are making the explanation of everything, as you can see. parameter, for example, numeric field of the vector layer. For label X, label for the axis X, label Y, label for the axis Y, and etc. Title of the graph, and then other interesting information is related to the creation. Okay, algorithm creation, that's the way we can add the author of the algorithm. Also for the helper, as you can see, with this kind of information, and also for the version, algorithm version, in that way. Okay, then we can save this one and close. And now let's go to make the final edition of that file over here. Click right on your mouse, rename, and here we are going to add point help. Now let's see where we want to save this file. Then go to QGIS again, go to the plugin, go to the script. The script is number 6, then click right, edit the script, and then press this option here, save as. Then here we are going to have the folder where all the scripts are saved. Then copy the link, and let's go to close this one, go here. Then what we are going to do now is paste the link over here, paste, and press enter to go to the folder, and it's number 6, is this one. As you can see, we have for each of these files, not for the ones we created, for these ones that we downloaded, we have always a RSX file and also help file. Then what we are going to add now is the help file for this histogram combines. Then let's go to copy this one over here, copy, and now let's go to paste inside this folder. Paste over here. Okay, it's over here, but as you can see now is a text document. Here we have a problem because we want to have a help file and now we have a text document. That is really important. If you go here, click right on your mouse, go properties, you are going to see that even the name of the file is like this. That one you cannot see the extension, because when you go to the tiles, you are going to see that the extension for this file is text. Okay, and we want to remove that extension because we want help as extension. But when we try to edit over here, rename, it is not possible because you cannot see text over here. Then what you have to do is go to control panel over here, then go to appearance, go to file explorer, then go to the tab view, and here you have this option, hide extensions for non-file types. Then you have to take the check out of this box, then apply and OK. Then as you can see now, properties or rename, now you can see the extension text, and we don't want that extension. Then we are going to remove that one. Yes. And let's go to copy this one. Copy, and let's go to this folder. Let's go to remove this one because this one is text, as you can see. Then I want to remove this one, delete, and I want to paste the new one, paste. And this one is over here at the top, number 6. As you can see now it's help over here and it's help over here. Now we can close this one, go to again to QGIS. Let's go to close this one and close this one again. And now let's go to open to see what we did. Number 6, double click. And as you can see now we have all the information we added in the help file. Even here at the bottom, we have the information related with the author of the algorithm, the help author, and also the version of the algorithm. That's the information we added. And we make a definition for all these parameters over here. And also the description for the script we created. Well, that's everything about the menu help for your scripts. And now I would like to show you how you quantify if your distribution of your data is normally distributed. To do that one, we are going to see a couple of tests. It's going to be the shapiro-Wilk test and also the Kolmogorov-Smirnov test. Okay, let's go to do it. Hey, do you know the Geo RGB community has a Facebook page? I'm going to leave the link at the video description, then you can click and follow us in this page. I'm going to be posting some content here that you are not going to see on the video tutorials in YouTube. Also, remember, if you want to have access to the scripts that we are using at the course, go to the Geo RGB community website, go to courses, then click on this course, start the course, and then go to the lesson. For example, for lesson 4, click on the lesson, and here you are going to have the attachments related to the scripts that we was using in this lesson. Remember that I'm going to post the scripts exclusively at the Geo RGB website. Okay, let's go to continue. We already saw 3 types of graphs that we can use to have a visual representation of our data distribution. It was the histogram, the box plot, and also the QQ plot. And also we saw how to calculate the skewness. That is going to help us to see also if our data is normally distributed. Remember that we want to know if our data is normally distributed or very close to the normality, because in some statistics techniques or statistic methods or models, sometimes we need to have our data normally distributed in order to cover the assumption to use that statistic techniques. Now I'm going to show you 2 more tools that you can use to check the normal distribution of your data. The first one is going to be the Shapiro-Wilk test. The Shapiro-Wilk test is a test of normality for a population with less than 50 samples. This number, you know, every author is changing this value. Some authors, they are saying that you can use that one for no more than 30 samples. Other authors, they are saying that you can use for less than 50 samples, and other softwares, for example R, allow you to use this kind of test for less than 3,000 samples. In this course, we are going to use the Shapiro-Wilk test for less than 50 samples, and for more than 50, we are going to use the Kolmogorov-Smirnov test. This is the mathematical expression to calculate the Shapiro-Wilk test, and is designated with the letter W. I'm not going to show you how to calculate that one manually, but you can make your own search on YouTube, and you are going to see some videos where people show you how to calculate that one with Excel. It's not really complicated. In our case, we are going to use R, and with R we are going to have the W value, and also we are going to have the P value. The P value is associated with the W value according to the number of samples you have. The p-value, it is essential in order to accept or reject the null hypothesis. But what is the null hypothesis? Okay, the null hypothesis, known as H sub 0 of this test, is that the population is normally distributed. Thus, if the p-value is less than the chosen alpha level, known as significance, then the null hypothesis is rejected, and there is evidence that the data tested are not normally distributed. And in that case, it's going to be the alternative hypothesis, and it's known as H1. On the other hand, if the p-value is greater than the chosen alpha level, then the null hypothesis, h sub 0, that the data comes from a normally distributed population, cannot be rejected. Alpha, that is the significance, used to be equal to 0.05, and that represents 5%. Then filing the normal test allows you to state with a 95% of confidence that the data does not fit the normal distribution. Here there is too much information and could be confusing. Then I'm going to make a summary, very simple. Then if the p-value is greater than 0.05, then we cannot reject the null hypothesis. Then we have evidence to say that the data is normally distributed. We have high probability, okay? Then if the p-value is less than 0.05, we have to reject the null hypothesis and then accept the alternative hypothesis. This alternative hypothesis say that the data is not normally distributed. Okay, that's it. And now let's go to see an example. First, let's go to create the script. Click here, create new script, and let's go to paste here what I did already. Let's go to make zoom to this one. That is a very simple script. You know, this one is about the group. You know this one because it's a vector layer, and this one is for the parameter we want to analyze. That is going to be, in this case, groundwater, and this is the script we are going to use. Okay, that's it. Then I'm going to save this one with this name. Going to cut this one because I don't want this one here, and then save as. Going to save in this folder, and I'm going to paste here the name. Paste and save. Then we can close this one, and if we go here, we are going to have the script number 17 for the Shapiro-Wilk test. But in this case, we have more than 50 samples because we have in total 57. Then what I'm going to do is remove 8 samples from here. Okay, going to close this one, and I'm going to close also this one, this card, because I want to create a new QGIS file. Then I'm going to open the CSV file. Okay, and I'm going to remove 8 points of data from here. Okay, I can remove the first, for example, 1, 2, 3, 4, 5, 6, 7, 8. Then I'm going to remove all these ones. Delete. Okay, and I'm going to save this one with a different name. Save as. And this one is going to be this one, but with 49 samples. Okay, 49. I'm going to add here 49 and save. And now I can close this one. Keep the current format, close, and I'm going to open again the QGIS. And I'm going to open that file. Then here I'm going to select this one, and it's going to be this one. Okay. The reference coordinate systems is good, the coordinates are good, and that's our data. Add and close. Now if we go to the attribute table, open attribute table, we have in total from 1 to 49. Okay, remember that in order to do the Shapiro-Wilk test, we want to have less than 50 samples. Okay, then I can close this one here. And before to run the script, the number 17 related with the Shapiro-Wilk test, this one, number 17, this one, I would like to add for this script the help menu. Okay, I have already here, I created already. As you can see, for this one I added the version, I added the description, the creator, the layer definition, the parameter definition, and the name of the script. Okay, then I'm going to copy this one here. As you can see, the extension is already good, it's help. Then copy. We can go here, click right, edit the script, select the folder, and we can paste directly here. Then paste, and that's it. Okay, then we can close this one. And now let's go to close this one also, and let's go to open the script to see if the things are okay. Number 17, double click. As you can see, now we have a description of the algorithm and also definition for the parameters and information related with the creator and the version. Okay, then here we have the layer, the vector layer, and then we are going to select groundwater. That's the parameter we want to do the Shapiro-Wilk test. Then run. And here we have the values. We have the value for the W and we have the p-value. As the p-value is greater than 0.05, we have evidences that the data has probability of being normally distributed. Okay, but this information, it's not enough to say 100% that we have a normal distribution. Then we have to support this information with a QQ plot, for example. Then I'm going to run the QQ plot over here. Then groundwater, and I'm going to fill these ones, but I'm going to pass the video faster. What I added here for the label X, it's normal theoretical quartiles, I mean quantiles. For the label Y, it's the observed quantiles for groundwater elevation in meters. The title of the graph is QQ plot, and the subtitle is going to be raw data because we didn't make any modification on the data. Then I'm going to run this one, and this one is the result. Let's go to make this screen bigger. And as you can see, the data it's pretty normally distributed. We have most of the points over here on the line. Here at the tails, they are off, but this one it's pretty normal. And in this area, it's not really good, but it's not that bad. Then we can assume that the data it's pretty normally distributed. Now let's go to see the Kolmogorov-Smirnov test. The Kolmogorov-Smirnov test, also known as a QGIS test, is a test of normality for a population equal or bigger than 50 samples. And here we have the mathematical expression. I'm not going to talk more a little bit these expressions. Just to have an idea, it's a comparison between the cumulative distribution function of an ideal normal distribution, that is the red color in this line over here, compared with the experimental cumulative distribution, and that is the blue line. The blue line, it is supposed to be your samples, okay, your data, and then it compares both cumulative distribution functions, and then it takes the difference, and the difference is the letter D. Then with that difference, it can take the p-value, and it works the same as the Shapiro-Wilk test. Then for a p-value that is bigger than 0.05, in this case we failing to reject the null hypothesis, then we have high probability to have a normal distribution. Then if the p-value is smaller than 0.05, and then there is evidence for rejecting of the null hypothesis and accepting the alternative hypothesis. Then in this case we can say that we don't have a normal distribution. Now let's go to see the script with QGIS. Then go here, create new script, and I'm going to paste what I did already. It's going to be this one, copy and paste over here. And again, this one it's a very short script. We know all these ones, and in this case we are going to use a different library. In this case it's going to be this one, and it's going to be an advanced version of the Kolmogorov-Smirnov test. It's going to be the Lily version, and this one is an improvement of the original one. Okay, then I'm going to save with this name. Going to remove this line over here, save as. Here, I'm going to paste that name over here and save. Now we can close this one, and I'm going to add, in this case, the data related with the Meuse River, okay? Then I'm going to add the shape file that we created the other day with the transformation and data. Then it's going to be data Meuse shapefile, this one, open and add. That one is okay, and close. Here in this attribute table, we have the value for the sink, but also we have the values for the data transformation that we did at the previous lesson. Then we are going to use the logarithmic base 10 of sink to calculate the Kolmogorov-Smirnov test. So let's go to run the script. Here, in this case, it's going to be number 18. This one over here, double click. We didn't add any help menu for this one. You know already how you can do that one. This one is this layer. Then, as I said, it's going to be this one. Okay. Then that one is going to take longer because the software has to install the no library. Is this one? Let me show you. Edit the script. Has to install this library, and it's going to take time. Okay. Then I'm going to pass the video faster. Okay, that's it. As we can see here, the p-value is smaller than 0.05. Then in this case, we cannot accept the null hypothesis. We have to accept the alternative hypothesis. That's indicating that our data is not normally distributed. Okay. Let's go to see the QQ plot, how it looks like. I'm going to fill this information, but I'm going to pass the video faster. In this case, I added the parameter that is going to be the logarithm base 10 of zinc concentration. Here for the label X is going to be the observed quantiles for the log 10 zinc concentration in ppm. Then for the label Y, well, this one has to be here. Sorry, I make a mistake here. Copy. This one has to be at the Y, and this one at the that it's opposite. Okay, I'm sorry. Then copy this one, and I'm going to paste over here, and I'm going to take this one over here, and I'm going to paste down. Cut and paste over here. Now it's okay. And then the title of the graph is going to be QQ plot, and the subtitle is going to be log base 10 zinc concentration in ppm. Then I'm going to save this one as a log 10 zinc. Okay. Save and run. And let's go to see the graph. Let's go to make this one bigger. And as you can see, the details are really bad. That's pretty normal, but even here at the middle, the dogs doesn't follow the line. Maybe here a little bit, but it's not enough to say the distribution is normal. Remember that at the previous lesson we was doing the histogram for all the transformations, and the logarithmic with base 10 for zinc concentration, it was the best one. I'm going to show you the graph here. That one is the raw data, and this one is the logarithmic transformation with base 10. This one is the square root transformation, and this one is the inverse. And we saw that the logarithmic with base 10, it was the best because the median and the mean were very close, and the skewness, it was not really bad, and it was the value closer to 0 if we compare with the other results, right? But even we make that transformation, and that transformation looks very good if we compare with the raw data, because the improvement from here to here, it's a lot. Even in this case, the data it's not still normally distributed, okay? But the important thing is that we make a big improvement from here to here, and that's the only thing we can do, right, to improve the distribution of our data. Then, for example, if we want to create a model with Kriging interpolation, if we want to estimate the values for a specific area related with our data, we are not going to use these values over here. We are going to use these ones. Even for a Kriging interpolation, the ideal scenario is to have a normal distributed data. We can use this data. We are not going to have the best result, but we are going to have a better result than if we are using this case, right? Then that's the goal, right? With your limitations to get the best result. Well, that's the end of this video, and it's also the end of the univariate analysis. I would like to know your opinion at the video description. You can leave some comments about how do you think about this part of the course related with the univariate analysis? Did you find this course interesting? Because if I have to do a second part related with the bivariate analysis, I would like to know what is the opinion of the people. That's it. Okay, thank you very much for watching, and see you on the next one.